Hello everyone and welcome to MakeLearn 360. So in today's tutorial, we are going to solve some couple of questions to prepare you for your strength of material exams. And I'm going to start with the concept of stress. All right. So please, if you have joined, kindly leave a message in the comment section. Hello, so that I can see. Within the next 5 minutes, I'll be starting. Thank you. All right. Okay, great. So we are going to start with the concept of stress. All right. So the first one will be the concept of stress. So number one, the concept of stress. The concept of stress. All right. Okay. So now I've got some couple of questions which I'll be solving with you. And then the idea is that whilst we solve the questions, you should be able to pick, some ideas. Okay. So let's look at our first question. All right. So thank you very much for all those who have joined. Thank you. So I think we can proceed. So let's look at our first question. All right. So then so let's say you have been given a question like this. All right. Let's say you have been given a question like this. So I have intentionally placed the answer there so that you can see the answers. But why are we getting the answers? So that is why we want to solve the question together. All right. Okay. So now let's begin. So first of all, let's read the question together. Okay. So a steel rod which is 2.2 meter long and must not stretch more than what 1.2 millimeters, sorry, when 8.5 kilonewton is what applied to it, and then knowing that what the Young's modulus, which is E, is what 200 gigapascal. Is that right? So how do I solve this problem? Okay, so this problem is actually axial loading. Okay, so for axial loading, this is what happens. So let's say that you have an initial rod which was like this. Okay, let's say you have an initial rod which was like this, and then with this rod you apply a force. Okay, let's say you apply a force or a load. Okay, now let's say that the cross section or the cross sectional area is A. All right, now what happens is that whenever you apply a load, in other words an axial load, so when we say an axial load, it means that it is passing through the axis. Now what happens is that because of the axial loading, what happens is that there is going to be elongation. All right, there is going to be elongation. So you realize that there is going to be, all right, so let me do it this way. So this is my force, and then there is going to be elongation. So in other words, there is the actual length. All right, there is the actual length, and then there is an extension. Okay, so this is the extension, and then I have the actual length. So let's go straight forward. Now the first equation is the first equation which you have to know is that stress, so stress is force divided by area. Let's call this equation 1. Okay, now one thing that you also have to know is that stress is equal to the Young's modulus multiplied by the strain. All right, and then so let's call this equation 2. All right, and then finally strain is equal to change in length all right, so strain is equal to change in length divided by original length. All right. So that is strain, change in length over original length. So three equations, okay? Three equations. Now, since since stress is force over area, then we can say that equation 1 and 2 are the same. So I can say that force over area is equal to the Young's modulus multiplied by the strain. Okay. All right. I can even say that since the strain is okay. So since the strain since the strain is change in length over original length, then we can say that so the force over the area is the same as the Young's modulus multiplied by the change in length all over the original length. So to put everything together, I can also say that the formula for the change in length is equal to the force multiplied by the length divided by the area and then Young's modulus. So this one can also give us, let's say, equation 4. Is that clear? So now let's solve the question. So coming back to the question, so now this question is saying that the steel rod is what, 2.2 meters. Okay, so in terms of millimeters, it's going to what? So the actual length L is what? 2.2 meters, which is the same as 2,200 millimeters. Is that right? So how did I get it? You just multiply by 10 to the power 3. Okay. Now that is the length. After getting the length, now he said that it must not what? Stretch more than what? 1.2 millimeters. Is that clear? Meaning that the extension, so when you say it should not stretch more than what? 1.2 millimeters, that means that the extension, so the extension, which is the change in length, is 2.2 millimeters. Is that clear? Now, one thing that you have to understand is that when we say the change in length, it is actually the final length minus the initial length. It is not the final length. Please take notice of this. When it says that this is the extension, this is not the final length, but rather the difference between the final length and then the initial or the original length. Okay. All right. So now we have the change in length as this, and then he said that the force is what? 8.5 kilonewtons. All right. Okay. So then we have got our force, isn't it? So now since we know our force, it means that we can go straight forward. Is that right? Since we have our force, we can go straight forward, right? All right. So then we can say that Sorry for the inconvenience. Please, can you hear me? Hello, please, we are back. All right. So please, I'm really sorry. I think there was a problem with the microphone, and now it's working. All right. All right. So I think we can continue now. Okay. So so then we got to the point where we were about to write the force, and then I think so the force was giving us what? So the force was giving us 8.5 kilonewtons. Is that right? Okay. So the force was giving us 8.5 kilonewtons. All right. Thank you very much. Thank you very much. Okay. Okay. Now, you know, from the question, we need to read carefully. It says that the Young's modulus was what? 200 gigapascals. Now, let me teach you a trick. Let me teach you a trick here. So, the Young's modulus, which is E, is what? 200 gigapascals. All right? Okay. Now, since so E is what? So E is 200 gigapascal. Now watch this. You are going to, okay, so let's go back to the question. Number one, it says, determine the smallest diameter that should be used. Okay, so determine the smallest diameter that should be used. Is that right? Okay, so if we are interested in diameter, then where can we get the diameter from? So we can get the diameter from where? From the area. Why? Because the area is given by pi times the diameter squared over 4. So it means that if we know the area, we can actually solve for the diameter. Is that right? Okay. Now, interestingly, we have been given some information. He said that the elongation should not extend what? More than what? 2.2 sorry, the elongation is 1.2. Sorry, my bad. You know, he said it should not stretch more than 1.2 millimeters. So the elongation is 1.2 actually. So the elongation is supposed to be 1.2 millimeters. Okay. All right. So now if the elongation is 1.2, then we can say that the elongation or the change in length is given by the force multiplied by the length divided by the area and then the Young's modulus. Is that clear? All right. Now we know the elongation as 1.2 millimeters, right? And we also know, so we know that the elongation is 1.2 millimeters. Now we know that the force is 8.5 kilonewton, and then the actual length is also 2200 millimeters. Now we don't know the area, but we know the Young's modulus E as what? So we know the Young's modulus E as 200 gigapascal. All right. Now, since the Young's modulus is in gigapascal, it is good to present it in megapascal. Why? Because we are dealing with millimeters. So that if you have megapascals and then you have millimeters, then it will actually cancel out. Okay. So let's start with this. It will be 10 to the power 3 megapascals. That's all. So whenever you have gigapascal, you can always write it as 10 to the power 3 megapascal. All right. Okay. So therefore, if I make the area the subject, okay, no, let me just put the values inside. So it's going to be 1.2 to be equal to 8.5 times 10 to the power 3, which is in kilonewtons, right? And then the length was given as 2.2 meters, which is the same as what? 2200 millimeters. All right. Okay. Now you divide this by the area, and then you multiply this by the Young's modulus, which is what? 200 times 10 to the power 3. Now watch this. Because we are in megapascals, we don't need to worry about millimeters. Let's take notice of that. Whenever you are working with megapascals, you don't need to worry about millimeters. So now let's solve for the area. So solving for the area, A is going to be what? 1.2. So this one is not strength of materials, this is change of subjects. Okay, so the area is going to be 1.2 multiplied by 200 multiplied by 10 to the power 3, and then you divide everything by what? So 8.5 times 10 to the power 3 multiplied by what? 2200. So someone should give us the answer for the area. No, let me check this again. Sorry, let me check this again. So 1.2 multiplied by 200 times 10 to the power 3 multiplied by the area is 8.5 times 10 to the power 3 multiplied by 2200. Oh, sorry. So then the area, so this is wrong. So then the area is actually going to be 8.5 times 10 to the power 3 multiplied by 2200 divided by 1.2 multiplied by 200 times 10 to the power 3. So please, someone should give us the answer. So pick your calculators and then convince yourself that what you are doing is correct. Please, what is the answer? All right. Okay. So someone has calculated the answer. Thank you. All right. Thank you. It means you are following. So please, the area. So someone did it, and then he had what? 77.916. All right. Let's assume he is correct. All right. But if you don't agree, please calculate it on your own. Now, since we have the area, we will just divide and get the diameter. So please go ahead and find the diameter. Don't forget that the area is pi d square over 4. Okay. compute so part B is saying that we should compute the stress. I'm sorry about the sound. So let's calculate the stress. Sorry. So the stress is going to be what? Force divided by area. The force is 8.5 times 10 to the power 3, that is to say 8.5 kilonewtons. And then the area, so the area is 77.916 millimeter square. 77.916. All right. Now, since you are dealing with millimeter square and then Newton, whatever answer that you get is automatically in megapascal. Okay. All right. All right. Okay, so please, what is the stress? Someone should calculate the stress for us. All right. So someone got the stress. Okay. So let's say 109.1 megapascal. Because you are dealing with Newton and millimeter squared, please, it is stress. So it is not newtons. It's actually megapascal. All right. You have to be careful about the unit. I hope the concept is clear. I want us to solve another problem. All right. Okay. So thank you. Let's look at another problem. Please, can you all hear me? Can you all hear me? I'm sure you can hear me. All right. So let's look at another question. Let's look at another question. All right. Thank you. Okay. All right. So let's look at this question. Please, let's look at this question. All right. So let's read it together. So a nylon thread is subjected to what? 8.5 Newton tension force. So we know the Young's modulus, and then the length of the thread increases by what? 1.1%. Okay. So we have to find the diameter of the thread, and then we should also compute, the stress. All right. So let's go straight forward. So this one, we were given the percentage increase, isn't it? So the best way to solve this problem is to, first of all, what do we know? So we know that it was increased by what? 1.1%. What does it mean? It means that, so what is strain? Number one, strain is change in length over original length. Okay. All right. Now he's saying that the change in length was 1.1%. In other words, what he is trying to say is that if I express the change in length as a fraction, the change in length by the original length was actually 1.1%. And what is 1.1%? So 1.1% will be 0.0 so 0.011, right? 1.1%. Okay. All right. So that is actually the strain. I hope it's clear. Now, having known the strain, what do we know again? So we know the force, all right, or the load. So we know that the strain is given by what? Okay. So this is what we know. The change in length, delta, is force times length area times the Young's modulus, right? Okay. And then um okay, but we know that the change in length over the original length will be F over what? AE. And this is what we know as 0.011. So you see the way the question was twisted. Now that you know this, you know the force, you know the Young's modulus. So you can say that the area was 0.011 multiplied by what? So 0.011 multiplied by, okay, let me take my time and do it. So the force will be 0.011 A times E. So that A will be F all divided by 0.011 times E. But what is the force? The force is 8.5 newtons. And then so 0.011 multiplied by the Young's modulus. Now the Young's modulus was given as 3.3. That is for nylon. So it will be 3.3 times 10 to the power 3. That is in megapascals. So that whatever answer that we get will be in millimeters. So what is the area here? So what is the area here then? What is the area? All right, thank you. So since we know the area, we can go ahead and find the diameter. So please go ahead and find the diameter. So 0.0234 millimeters squared. Therefore, the diameter will be the square root of 4 pi. 4 times the area over pi. Because we know that the area is pi d squared over 4. Therefore, d will be square root of 4a over pi. Alright. So then the diameter is nothing but the square root of 4 multiplied by the area, all divided by pi. And what's the answer? Okay, so after getting the diameter, I think everybody can calculate the stress, right? What did you get for the diameter? All right. I think it's simple, right? Please, are you sure with your answer? 0.175 millimeters. Because if you take the square root of 4 multiplied by 0.0234 divided by pi, and you said you got 0.175. All right. Okay. Now, if we want to calculate the stress will be force over area. And the force is what? So the force is 8.5 divided by the area, which is 0.0234 Newton millimeter squared. So whatever answer we get, it will be in megapascals. Okay. So it's simple, right? It's very simple. Okay. So that is it for the for this question. It's kind of simple and straightforward. Let's see a difficult question which sometimes comes under this type of questions. Let's see if we can solve this one. Okay, thank you. You have the stress. Let's look at a question where you will be given okay. So please hold on for the next question. Okay, let's look at this question. Okay. Please, I hope you can see the question. All right. So this is some of the questions that confuses the students a lot. So let's see how we can solve this type of questions. Maybe let me make it big enough so that you can see it. Okay. All right. I hope you've seen this type of question before. So how can I solve this problem? All right. So it says that a single load of magnitude P, which is what? 58 kilonewton, is applied at the end of at the end C of the brass rod ABC. Now, knowing that E is what? 105 gigapascal, determine the diameter of the portion BC, for which the deflection of the point C will be 3 millimeters. What a nice question. Okay, so how can I solve this problem? It's pretty much simple. Now, the first thing which you have to do for a problem like this is, first of all, So let's take down some values. So there is an axial load P giving us what? 58 kilonewton. And then this load is applied at portion BC. But let's not forget that the entire ABC is brass, which means that the Young's modulus is actually applicable at any point along the section, because it's actually a brass rod, and the Young's modulus is giving us 105 gigapascal for this problem. All right. Okay. So we are to determine the diameter of portion BC, for which the deflection of the point C will be 3 millimeters. Is that right? Okay. So let's solve it together. Now the first thing we have to do is that since the load is the same and the material is also the same, the first thing we can say is that the total deflection, let's call it delta, at point C is going to be what? The deflection in AB plus the deflection in BC. Is that right? So basically what we are trying to say is that since AB and BC are connected together, if I apply a load P at C, then what will happen is that there is going to be deflection at C, and the total deflection is actually the deflection in AB plus the deflection in BC. I hope the concept is clear. But what is deflection? Earlier on we said that deflection is what? Force. Okay, so this time they said the force is P. So force times length divided by area times Young's modulus. I hope the concept is clear. Sorry. All right. So right now we have the okay, let me go back. Okay, so now one thing that we have to understand is that for this question, the same material, therefore if I have okay, this is what I'm trying to say. So delta C will be PL over AE of section AB plus PL over AE of section BC. But what I'm trying to say is that, you know, the axial load is applied to the whole member. All right, so they will all see the same P, and then also, you know, the Young modulus is the same for brass. So it's like the only thing that will change is that the length and the area that will change. So basically it is the length and then the area that will change. All right, so I hope the concept is clear. So for this one, we know that the length of AB is 1.2 meters, and then okay, let me write it. The length of AB is what? 1.2 meters, and then the diameter of section AB is what? So the diameter of section AB is 30 millimeters. So I think we need to choose one convention. So 1.2 meters can be the same as 1200 millimeters. And then for section BC is going to be the length of BC, which is what? 0.8 meters, which is the same as 800 millimeters. But the diameter of BC, in fact, that is the question. That is the question. He said we should find the diameter of portion BC. So let's call that diameter D. Okay. Let's call that diameter D, the diameter of the portion BC. But what do we know? We know that the deflection at C is the total deflection from what? Deflection in AB plus the deflection in BC. So at this juncture, we are just going to substitute the values. Okay? We are just going to substitute the values. And then we will be able to solve. But then the concept is clear. The only thing which you have to do is that in this case, since we want the diameter, I think it is best to make okay, let me do this. So I want us to do this. Let's multiply both sides by E over P. So it's going to be E over P. This multiplied by delta C should be equal to what? The length over the area for AB plus the length over the area for BC. But since we want BC, let's make BC the subject. It's going to be E over P delta C minus L over A for what? AB. Okay. So now let's solve this. So L over A for BC is going to what? E over P. Now, so let's go back. So what is E over P? So we want to substitute the values actually. So the Young's modulus E is 105 gigapascal. So you come down here and then so 105 times 10 to the power 3. Is that clear? All right. So then that is the Young's modulus. Please, we are going to deal with millimeters. So leave all the megapascals. I'm sorry. Convert the gigapascal to megapascal because we are going to deal with megapascals and millimeters. Okay. So we know E as that. We know P. What is P? So P is what? The load. And the load was what? 58 kilonewton. Okay. So that's the load. So 58 times 10 to the power 3. That is the load. Okay. And then the question said that the deflection will be what? 3 mm. Is that right? So the deflection will be 3 mm. All right. Please, let's take notice. The question said the deflection at point C. Is that right? So that is why we added the deflection in AB plus BC. Okay. All right. So now let's go back to the equation. Deflection is 3. So multiply by 3 minus the length divided by the area for AB. Now the length of AB is 1200 millimeters. All right. And the diameter is what? 30. So it's going to what? 1200 over 30. Okay. So 1200 divided by what? 30. All right. Okay, so someone has something in the comment section. Yeah. So the answer was what? 0.55 millimeters. Thank you for correcting it. Yeah, it's correct. Thank you. Thank you. It means you were following. All right. So let's continue. So now that we have everything that we need, so okay. So now someone should compute this for us. The length over the area for BC. And then punch everything here on the calculator. What are you going to get? Someone should do that for us. So what is the ratio of the length over the area for BC? So this is the last question I'm solving on this type of problems. There are several types which I would urge you to actually spend some time and then solve. So I'm waiting for the answer. Anyone to help us? Hey, you had negative. How? Please check your answers well. Okay, so to avoid any confusion, okay, so to avoid any confusion, let's rather do this. To avoid any confusion, let's rather do this. So 105 multiplied by 10 to the power 3. Okay, let me just make it gigapascal so that I don't confuse anyone. Then I'll multiply here by 3 times 10 minus 3 divided by 58 times 10 to the power 3. That one is in kilonewton. Minus, so 1.2 divided by, so 1.2 meters divided by 30 millimeters. So 30 times 10 minus 3. Okay, so please do it again and let's see what you get. So in this case, we are dealing with meters. All right. So what is it then? Please, let's hurry up. From here, I want to do torsion and bending. Okay. Okay. So another answer is in. So 5431.034. Okay. All right. Okay. All right. So now we have this. So the question said we should find the diameter. Look at this. The question said we should find the diameter of the portion BC. It means that we need to go back and then solve for the diameter. Now this is how we are going to do it. So now we can say that the length AB, the length BC is what? 5431.034 multiplied by what? The area of BC, right? But what is the area of BC? So the area of BC is going to be the pi d square over 4 BC. And in fact, that is how we can solve for the diameter. So length of BC will be 5431.034 multiplied by the area, which is pi d squared of BC all over what? 4. From here, we can go straight forward. We know that the length of BC is what? 800 millimeters, which is 0.8 meters. So then, okay, let's make the BC the subject. It's going to be okay, let me take my time. So 4 times LBC will be what? 5431.034 pi dBc squared. Therefore, dBc is going to be the square root of 4 times LBC, all divided by what? 5431.034. And that's what? 4 times 0.8 divided by 5431.034, and that is the diameter of BC. I hope the concept is clear. What is the diameter? All right. So what then is the diameter? Okay. All right. So someone has calculated the diameter 0.024 meters. All right. All right. I hope the concept is clear. So I want us to look at so these are type of questions that normally comes. You may get, several of some of these questions, but then I want us to look at quickly the shear force and the bending moment diagram. It's very important. But there is a question here which I want to go through with you. Okay. So let's look at this question. I want us to look at the shear force and the bending moment diagram. Okay. Are you ready? In fact, if you're able to understand what we are about to do right now, I must say that you have already passed. If you're able to understand what I am about to do with you right now, you have already passed. Okay, so then let's begin. So whenever you are given a question and then you have been asked to draw the shear force and the bending moment diagram, this is where you start from. Number one, find reaction forces. So in this case, the reaction forces have been given to you, but I will go through quickly how the answers came about. And then number two, after solving for the reaction, draw the free body diagram. In fact, if you don't draw the free body diagram, you cannot even solve for the reaction. So this one and this one, they go hand in hand. Okay. And then, okay. I think these are the two steps first. And these two steps are actually equilibrium of a rigid body. Equilibrium of a rigid body. All right, so let's start. How can I find the reaction forces? So we want to show that it is 18 and 24. All right, okay. But sometimes the question can be complex. But for this problem, I want us to solve this so that it will give you a fair idea about or of how we solve some of these problems. Okay. So now okay. So let's start. The first thing that you have to know is that there is a pin joint at A. Okay. And because of the pin joint, there is going to be what? Two reactions, right? And then these two reactions, so let's call them AX and then let's say AY. Let's say AY is coming down. And then at point D, there is a ruler. For a ruler support, there is only one reaction. Let's call it dy. Okay. Now, after getting your reaction forces, this is what you are going to do. So in fact, this is the free body diagram. Okay. All right. So, what are the conditions for a rigid body to be in equilibrium? Summation of force is 0. Summation of moment is 0. Now, starting with the summation of force along the x, every force in this direction should be 0. So we realize that minus ax is 0. In other words, ax is 0. So technically speaking, there is no force along the x. That is what it means. Okay. So we've been able to show that ax is indeed 0. All right. Now, how do I put it? For the y, basically, summation of forces, every force going up is positive, should be 0. Okay. Now let's go back. We said that AY is coming down, isn't it? So it will be negative. So minus AY minus 14 kilonewton minus 28 plus dy equals 0. So minus 14 minus 28 plus dy is equal to 0. So in other words, minus ay plus dy is equal to 14 plus 28. What is it? So 14 plus 28 is 42, right? So let's call this equation 1. I hope you are okay. Okay. So now, so this is equation 1. Let's start with moment, or let's go to moment. So for moment, summation of moment is 0. Okay. All right. So now we will go back to the diagram, and then we are going to some moment. So we can either stand at A or D. So I want us to stand at A and take moment about A. All right. So now, because we are coming to take moment, we can say that clockwise is positive. All right. That is a convention. Is that right? Okay. So then, starting from A, so moment is force times distance. Is that right? So 14 kilonewton multiplied by the length. All right. And what is the length? From here to here is 2. So 14 times 2. But what is it? Is it clockwise or anti-clockwise? All right. So because the force is coming downwards like this, it will create a clockwise moment about A, right? So it's going to be plus 14 times 2. So 14 multiplied by 2. Then we will move to the next force, which is what? 28 kilonewtons. All right. Now this 28 kilonewtons will be multiplied all the way by the distance, right? Which is what? 28 times 5, right? So that's 28 times 5. Okay. So 28 times 5. And that is also clockwise about point A. It is clockwise. All right. Now, because 28 times 5 is clockwise, it was positive. But this time around, we are going to do dy. All right. And dy is coming upwards like that. We said that dy is going up. So then if I multiply the entire distance all the way to A, that distance is what? 2 plus 3 plus 2, which is what? 4. So 24, which is 7. 24 times 7. But watch this. The direction is in this sense. So dy multiplied by 7, right? But it is what? Counterclockwise. So it's going to be negative. So minus 24. Minus 7 dy is 0. So minus 7 dy is 0. Therefore, we can say that dy will be 14 multiplied by 2 plus 28 multiplied by 5, or divided by 7. So someone should calculate dy for us. All right, so what then is dy? All right, 24. Thank you. It means they are following. So you see that dy is what? 24 kilonewtons. And that is it. The reaction at D. So I didn't just use it like that. I wanted to show you where it came from. So before you even do any question on shear force and bending moment diagram, you need to find the reaction first. And if you're able to find the reaction, in fact, you have gotten some marks here. Okay? So that's why I'm saying that if you're able to understand what we are doing on this question, you have passed already. All right. So now we'll go back. We'll go back to equation 1 and put dy inside. And what are we going to get? So dy will be what? 42. Oh, sorry, ay. So ay is going to be dy minus 42. And what is that? All right. So 24 minus 42, which is minus 18. You know the reason why it's minus? It is minus because we assume that the reaction at A is coming down. Meanwhile, it was going up. So that's why we got negative. So it means we have to go back and put the reaction at A. I think it's already there. So this is the first step. All right, so we are done with the first step. So the first step is to what? Find the reaction forces. We've now been able to do that. Okay. All right. So then now this is where we start. Okay. I will close at the end of this question. And then if you have a question, you can see me. Yes, Stephen, you are right. So whenever we get negative, it means the direction we chose was the opposite way. And then when we started, we said it was coming down. So right now it is negative, meaning that we have chosen an opposite direction. Okay. So that's why we have changed it to go up. All right. So AY will now be what? 18 kilonewton. All right. So this is where we begin solving the question. So let me even copy it and bring it here. All right. So our question is here. Now we know all the reaction forces. So we are coming to draw the shear force and the bending moment diagram for this question. Then we close. And then if you have any other question, we can look at it. All right. So to begin with, we are going to take, okay, so this is how we do it. We are going to take each section. So we have A, B, C, and D. All right. So we will take each section and cut a portion. So this is what we are going to do. They have already done it for us. So between A and B, you will take a section. Okay. Now let's see what happens when we take a section. So let's say I have A and B, and then I decide to take a section. This is what will happen. So whenever you take a section, for the purpose of time, the question has been solved already. So I will just explain and solve it together with you. So if I take portion as segment, if I take segment AB, okay, if I take segment AB and then I take some portion, this is what is going to happen. Okay. All right. Please, I have done a full video on free body diagrams, so I will share the link so that you can watch that video. I think it will help you. It's a full video on free body diagrams. Thank you. All right. So please, so let's take notice of this. Whenever you take a portion, you will bring a movement in this direction, and then shear force will come down. Let me do it this way. So shear force will come down and movement will go this way, always, whenever you cut a section. So now we are going to assume that this is actually a rigid body in equilibrium. All right. So if a rigid body, is in equilibrium, summation of force will be 0. So let's sum forces. Every force going up is positive, to be 0. Okay. All right. Okay. So what forces do you see? 18 kilonewton minus V, because don't forget that V is coming down, should be what? 0. Which means that V is what? 18 kilonewton. Is that clear? Now what does this tell us? So what does this tell us? It means that if I take a portion and cut from A to B, the shear force is constant. It does not depend on X. That's the meaning. All right, let's look at the moment. Let's be quick here. So for the moment, we are going to some moment about X. Okay. Taking the moment, this is what we are going to get. So summation of moment about, let's say, point E, clockwise is positive, should be 0. Is that right? Okay. So taking the moment, we can see that um 18 multiplied by X. Now when we say X is like this one. So we have taken a portion and we are calling the distance from here to here x. Is that right? So think about x as a portion that you have taken. Summing the moment, 18 multiplied by x is actually going this way, which is what? Clockwise. So 18x. And what else? There is this moment which is going counterclockwise. Alright? So minus m to be what? 0. This means that what? M equals 18x. Alright. So put these two equations down. Write it somewhere. Now let's come to the second portion. But we need to understand that what we have cut here is valid for x from 0 to 2. Or let's say x between 0 and 2. Alright. Okay. So then let's take the second portion. If you stand at, if you stand between B and C, cut. So if you stand between B and C, and then you cut. Okay. This is what you are going to get. Please, I hope you can hear me. Can you hear me? Can you hear me, please? Okay. All right. Okay, thank you. So now we are coming to the next portion, which is portion BC. Now please watch this. You are cutting something like this from here. Okay, this is what is going to happen. You have 18 kilonewtons reaction force here. All right, and then at a distance 2 meters, you have 14 kilonewtons at a distance 2 meters. So it means that if you move away from the 14 kilonewton and cut, you are going to measure a distance x all the way. So the x this time is all the way from the starting to where you have cut. So basically, think about it as this. So starting all the way from where you have cut. So from the origin all the way to this point. Okay. And let's call that x. So now we know that from here to here is what? 2. But we don't know the distance here. Meanwhile, we know from here to here is what? X. Right? So if this is x, and then from here to here is 2, then this small distance away from 14 to this point, we can call it what? X minus 2. I hope the concept is clear. So that is what we have here. The whole of this is x, and this is 2. So away from the 14 to where the x is, we can call this x minus 2. All right. Okay. And don't forget that always the shear force will come here, coming down, and the moment will go counterclockwise like that. Always. Okay. All right. So now we are going to sum forces again and sum moment. So summation of forces, every force going up is positive, should be 0. Is that right? So from here, we can say that 18, which is going up, 14 is coming down, so minus 14. V is also coming down, so minus V is 0. From here, V equals what? 4. All right. So we can say that the shear force is 4 kilonewton. But please take notice, the 4 which we have got is valid from where? 2 and 5. Why 2 and 5? Let's go back. You see that from the diagram, from here, if I take a cut, which is somewhere here, it will always be between what? 2 and then what? 5. So 5 is like 2 plus 3, which is up to here. And then 2 is from here to here. So if I take a section here, it will always be between 2 and then 5. And that's what we are saying. Okay. Now let's look at the moment. So for the moment, please open your eyes. So summation of moment about E should be 0. Clockwise is positive. All right. Okay. So with this one, the 18. So we are going to take moment about, F. So F is like that portion here. All right. So it's going to be 18x. But is it clockwise or anti-clockwise? It's clockwise, because this 18 kilonewton we'll move it that way. But the 14 kilonewton about F, what is the moment arm? Everyone watch here, please watch here. The distance from here all the way to the section is x, but from here to a 14 kilonewton is 2. Therefore, the remaining distance will be what? The difference between what? X and 2. And that is the reason why from here to here is what? X minus 2. Alright. So for the 14 kilonewton force, it's going to be counterclockwise. Why? Because we are taking moment about this section. So it's like this. You have something like this, and the 14 kilonewton is coming like this. So it's going to cause the moment to turn it in that sense, which is what? Counterclockwise. So minus 14x minus 2. Please, you have to take notice of this, right? Once you interchange it, that is the end of you. So you need to be very careful about that. All right. Okay. Is there any other moment? So this moment M here is counterclockwise, right? So minus M to be 0. What does it mean? It means that M is what? 18x minus 14x plus 14 into 2, right? So basically M is what? 4x plus 28. So this one too, write it somewhere. So for all the sections that we are going to take, we'll look at the shear force and we'll look at the bending moment. It's very important. All right. So finally, we need to cut. All right. So we started from here. We did the first cut, which was between what? 0 and 2. Now we did the second cut, which is what? So let's say this is 0. Sorry, this is 0. This is 2. This is 5. This is 7. Okay. So we did a cut between 0 and 2. And now we have done between 2 and 5. So now we are about to do between 5 and 7. And this is how it's going to be. You will stand here and cut like this. And that is what they have done as 3. Meaning that all the forces here will come into play. So let's see how it goes. All right. So it's going to be like this. And look at it carefully. You can see that from 0 to 2 will come in. And from 2 to 5 will come in. But the portion that we have taken is between what? 5 and 7. I hope it's clear. So we have taken a section between 5 and 7. Which is this? you know, the section is far away from 28 kilonewtons. All right, but it is not at 24, so it is like it is between 28 kilonewton and the reaction at D, which is what? 24. Okay, so let's not forget our shear force and then the bending moment. Sorry. Again, summation of forces. Every force going up is positive, should be 0. So we are going to get something like this: 18 minus 14. So you know 18 is going up, that's why it's positive. 14 is coming down, minus 28 because 28 is coming down. V is also coming down, so minus V is 0, which means that V will be what? It means that 18 minus 14 minus 28, which is what? Minus 4. So V is what? Minus 4. All right. Let's do the same for the moment. Now, for the moment, this is how we are going to do it. For the moment, so let's start with the 18 kilonewton. So 18 all the way from here up to J. So it will be multiplied by X. Is that right? Okay. Now after doing this, then you come to the 14. Okay, let me take my time. We are summing moment about point J. Clockwise is positive, should be 0. But the 18 is clockwise, that's why it's positive. Then the 14, you can see that. Okay, so let's watch this carefully. From here all the way to here is X. Therefore, if here is 2, then from 14 to where the J is will be X minus 2. I hope the concept is clear. All right, we know that from here to here is 2. So then if here is X, then from here all the way to J will be what? X minus 2. So for the 14 kilonewtons, the moment arm or the distance will be 14 times S minus 2, which is what? Minus. Why is it minus? Because it is going to be counterclockwise. Okay. Now, interestingly, watch this. You will see that from here all the way here is 3. And then from here all the way here is 2. So 2 plus 3 is 5. Now the question is, if all the way from here to here is 5, but then you see that the portion which has been sectioned is away from the 5. Therefore, what is this small distance? This small distance. Okay? And that small distance must be what? X minus 5. In other words, from here to here is X, and then this is 2 plus 3 is 5. So beyond that, all the way to M or J, sorry, is X minus 5. And the moment that the 28 kilonewton create is going to what? So it's like something like this. I will have the force here as 28, and the distance will be X minus 5. So the moment is going to create a moment in that sense, which is counterclockwise. X minus 5 to be 0. Okay. So it's going to be 8. Oh, sorry, we didn't add the moment. The moment is counterclockwise, so it's going to be plus moment to be 0. All right, so 18x minus 14x plus 28 minus 28x plus 28 times 5 plus m to be 0. In fact, if you do everything correct, you realize that m will end up as minus 24s plus 168. So minus 24x plus 168. All right. So please, okay, minus m. Yeah, thank you. It means you are following. But it doesn't change the answer because I have done it. So 18 minus 14 minus 28 will give you the minus 24s, and then 28 plus 28 times 5. That was that is 168. Okay, so guys, we are done, but we are not done. We are done because we have the shear force and the bending moment, but we are not done because we need to draw it. Please check it well. It's supposed to be plus 168. Okay. All right, so let's start. So this is where we actually start solving the question. Interesting. Because we know everything. So this time we are not going to struggle. So for the purpose of time, I will go straight forward. Thank you for checking. All right. So guys, we are almost done. All right. So there we are. I want to make it big so that everybody will see it. I'm sure everybody can see it. All right. So when we say the shear force is a diagram. Sorry, the shear force diagram is a diagram which shows the distribution of the shear force. That's all. Oh, sorry. Okay. So let's assume that our zero axis for the shear force is this. Okay. So we are done. We will go to section A and B. What was the first value we got? So let's come here. Okay. So the shear force was what? 18. Right? So when you come to the diagram, you just illustrate 18. That's all. And it was constant. So it means that the shear force was 18 thrown out from A to B. That's all. In kilonewton. That's all. And then you will go back to the first one again. Okay, let's finish shear force. Then we come to moment. So we are done for section A, B. Now after cutting between B and C, you realize that the shear force was what? 4. It means that the shear force between B and C reduced from 18 to 4. Is that right? So it reduced from 18 to 4 kilonewton. That's what it means between B and C. And finally, between okay, please, I think someone did a correction here. I didn't check. It's actually minus 24. So 18 minus 14 minus 28 is minus 24. All right. So basically, it means that the shear force came down and then it exceeded the zero line all the way to minus 24. So minus 24. So we are done. So now this is the plot of the shear force. That's all. Please, any question? All right. So now we are going to draw the bending moment and then we'll end. Okay. So let's draw the bending moment and then we will go. So for the bending moment, I can also create an arbitrary axis. But sometimes in the exams, you may be given a graph sheet. And the graph sheet, you have to draw it to scale. So it depends on the examiner. Sometimes they can say sketch. Otherwise, you'll be given the drawing sheet. Okay. So let's say that the zero line for the bending moment is this. So moment or kilonewton meter. And let's say that this is the zero line. Is that okay? All right. So this is let me take my time. This is the moment. All right. Between A and B, the first section, the moment was what? 4x plus 28. Now I want you to think about this not as moment, but think about it as a straight line. Okay? What is the equation of a straight line? So the equation of a straight line is y equals ms plus c. So y equals ms plus c. If you compare this to equation of a straight line, you can say that what you have here is actually a straight line. Is that right? But the slope of the straight line is 4. And the y-intercept is what? 28. So simply put, this is a line with slope 4 and the y-intercept of 28. To draw this, technically it means that our moment is a straight line which is moving from 0 to 2. All right, don't forget that the first section, oh sorry, I'm sorry, the first section is 18x. Oh, my bad. I was trying to explain the second portion. The first section is 18x. That is the moment. Sorry for that. Okay, so you can think about this as a straight line, y equals mx plus c. But this one, the y-intercept is 0, right? So it means that if I draw the straight line at x equals 0, the moment is 0. But at x equals 2, the moment will get a value which is what? 18 times 2. And what is that? 36. So this is what I'm trying to say. If you put s equals 2, you are going to get 36. So simply put, this is 36. but then it is actually a straight line. All right, and the equation of this straight line is 18x. I hope it's clear. All right, so then we are done with the first portion. Now let's come here. So this is where I was trying to explain. The moment function here is 4x plus 28. It means that we are not going to start at x equals 0. Why? Because the section was between 2 and 5. So if you want the minimum, we are going to start at where? S equals what? 2. Please, I hope it's clear. The segment is between 2 and 5. So if you want the minimum, we are going to start at where? 2. And then come to where? 5. Another way to interestingly think about this is that you have a straight line of slope 4 and intercept 28. All right. Let's do something here. You will see that this is pretty much simple. So 4 multiplied by 2 plus 28. What is it? This is 36, right? Is that not interesting? 36 is already here. So it means that this line will start here. I hope it's clear. All right. Okay. So let's put the value of, it is moving from 2 to 5. Let's put 5 inside and let's see what we will get. If we put 5 inside, what are we going to get? If you put 5 inside this, it's going to be 4 times 5 plus 28. And what is that? Someone should help us. So 20 plus 28 is what? That is 48, isn't it? Okay. So it means that we have a straight line which is moving from 36, but it will come here and cut this line, and the magnitude at this point where it cut the line is actually 48. Thank you. It's correct. But let's not confuse the shear force with the bending moment. All right. So we are done with the second part. Okay. Now let's come to the last part. Let's come to the last part. You will see a magic very soon. You are going to see a magic very soon. So please open your eyes. You will see a magic very soon. For the third portion, we took a cut between what? 5 and 7. Right? So for the minimum value, okay, again, think about this. The moment function is what? Minus 24x plus 168. So the minus sign here is what? What do you think? Whenever I have equation of a straight line and the slope is negative. Oh, I've said it. If the value here is negative, then it means the slope is negative. If slope is negative, what do you think will happen? Instead of the line going up like this, it will rather fall. Is it clear? Meaning that we expect the slope to decrease. Oh, sorry. We expect the line to fall as it moves from that point. Okay. So everyone, put x equals 5. So it's going to be minus 24 times 5 plus 168. Please, what is it? Minus 24 times 5 plus 168. What is it? Very good. Very good. Now I want to shock you. I will not tell you the answer. So we said that between 5 and 7, right? Okay. So if that is the case, put 7 into the equation. You want to get the value at x equals 7. I will not tell you. Put 7 here. So what is it? So the moment at that point, minus 24 times 7 plus 168. Type the answer there. 0. Thank you. Thank you. Thank you, Emmanuel. Oh, you're also Tata Emmanuel. Yeah. Thank you. What does it mean? It means that the moment function is a line, and this line is having a slope of minus 24. So you see that it is decreasing, and then it decreases to 0 at x equals 7. That's all. So this is the line. That's all. All right. So that is our bending moment. That's all. So we are done. That's all. This is our bending moment diagram, and this is our shear force. Shear force diagram. All right. So we are done. I hope the concept is clear. All right. So thank you guys for joining. If you have a question, you can let me know. Sorry. And then I will also share the other links